Hello everyone, I am Sanket Singh and welcome back to my channel. So guys, in this particular video, we are going to do some problem solving around loops. We already discussed the concepts of loops in our free JavaScript playlist. And now I believe it's a good time to actually start our discussion on how we can actually do looping in JavaScript and try to solve some problems around that. You already know about for and while loops, and this might be a great opportunity for you to actually brush up all of those concepts and also do some hands-on problem solving around them. So without any further delay, let's just start. But before starting the video, if you have not yet subscribed to the channel, do consider subscribing to the channel. We are going to put some really awesome content up ahead on this one. So let's just start. So guys, before moving forward, there is a very important information that I would like to give you. So recently we wrapped our Elite 1.0 front-end development course, and now we have launched our Elite 2.0 advanced front-end development course. This is a bigger and a better front-end development course that you need. This course doesn't need any particular prerequisite, and we are going to take you from the very beginner level to the advanced level of front-end engineering. We have actually included projects like your own Replit clone, Wix website maker clone, right? Uber clone, and a lot of similar projects. You are going to make your own PubSub library based LLD driven projects, and we are going to make sure that you learn important front-end design patterns as well. I'm going to list down all the projects and all the important design patterns here. This is the only course that you need if you are aiming for SD1 or SD2 or SD3 kind of roles, because we are going to take everything to the very advanced level in front-end engineering. We are going to learn a lot of optimizations, and we are going to see technologies like Next.js, Redux, Zustand, TypeScript, React, and of course, the latest version of React. This particular course is going to make sure that you have ample amount of projects that you can add in your resume. We are going to make approximately 20 plus projects with different variety of complexities, engineering problems, and of course, there will be a lot of discussion around the core concepts of frontend. So what are you waiting for? Check out the course link in the description below, and you can use the coupon code mentioned in the description section to get maximum discount possible. See you guys in the cohort, and let's get back to the video. So in our problem solving journey, we have a new question in front of us. This question is to calculate GCD of two numbers. Okay. So you are given two numbers A and B, and you need to find the greatest common divisor of A and B, right? You need to find the greatest common divisor. Okay. A lot of time you will find this term greatest common divisor also called as GCD. And in your elementary classes, you might have referred it using HCF, which is highest common factor. So all of these terms are same: greatest common divisor, GCD, highest common factor, HCF, all of these are same terms, right? The meaning is which value or which divisor is the biggest divisor that can divide both of the given values. Okay, that's the actual essence of the question. So for example, if let's say the first number is 28 and the second number is 24, then the answer is going to be 4. 4 is the first common divisor, or I would say the biggest common divisor, technically biggest common divisor that can divide both of them. Okay. So how can we solve it? How can we solve it is something that we are going to take a look at. If you go to elementary classes, then if I would have asked you that one number is 28, another number is 24, calculate the greatest common divisor of the both of the things. So how you would have calculated? Let's see. So you would have written the factors of 28, that is 2 into 2 into 7. And you would have written factors of 24, that is 2 into 2 into 2 into 3. Right? These are the factors of 28. These are the factors of 24. And then what you would have done? You would have calculated that this is the common factor, which is what, 2 into 2, which is 4, and hence 4 is the answer, because 4 is the biggest common value that can divide both of them because they are available in their factors. This kind of an approach you might have developed in your elementary classes. But can we solve this question using this approach? I believe yes, but currently whatever knowledge we have in programming, we just know about basic variables, if else, and for loops. We don't know that how you will be able to store a list of these numbers and how you can calculate the intersection, or I would say common values from those lists. We don't know about storing multiple values together, right? So technically at this point of time, this approach might make sense, but it's not feasible for us to be able to code it. Like you need to somewhere store something like 2 comma 2 comma 7, and somewhere something like 2 comma 2 comma 2 comma 3, something like this we need to store. But currently we don't know anything using which we will be able to store multiple values together, right? So that's why we are going to discard this approach for now. But yes, this approach makes sense once we have all the required tools that we are going to learn later in the cohort. Now what we can do, what to do now? So in order to understand what to do now, we will go to the core definition of GCD. What is the core definition of GCD? GCD means greatest common divisor. That means there is some number, or I would say some biggest number, that can divide both of them. Now you tell me one simple thing. Now you tell me one simple thing. Why 2 is not the answer? 2 can divide 28, 2 can divide 24 also, but 2 is not the answer. What do you think is the probable reason? Because we want to have the greatest number that can divide both of them, or the highest number that can divide both of them. Can I say that? See, 2 can divide 28 also. 2 14s are 20, 2 14s are 28. 2 can divide 24 also. 2 12s are 24. Right? So what I can say is that 2 can also divide both of the numbers completely, but 2 is not our answer because we want the greatest common divisor. We want the biggest number that can be the common divisor. Okay. Can 3 be our answer? 3 can divide 24 correctly, but 3 won't be able to divide 28. So 3 can never be the answer. Can 4 be the answer? Yes, you can see. 4 can divide 28. 4 can divide 24. So 4 can also be the answer. Right? And so on and so forth, and so on and so forth. So what I'm trying to say is we want to detect a number that can divide both A and B. We want to detect a number that can divide both A and B, right? There can be multiple numbers that can divide both A and B, right? There can be multiple numbers that can divide both A and B. Among those multiple numbers, we need to get the biggest one. We need to get the biggest number. Can I say that? So if I take an example of 28 and 24, right? And here I am going to write potential answer. I'm going to write a potential answer. Potential answer means something that can become our answer. Okay, cool. Now we don't consider 1 in the highest common factor because 1 can divide everything, right? So 1 currently I'm not going to consider. So although 1 can be the answer in case of like prime numbers, like what is the biggest common factor between both of them? It's going to be 1. But let's don't consider that corner case for now. Let's try to think simple. Let me ask you first question. Can 2 divide both A and B? Can 2 divide 28? Yes. Can 2 divide 24? Yes. How will you check whether 2 can divide 28 and 2 can divide 24 or not? You will check whether 28 mod 2 is equals to 0 and 24 mod 2 is equals to 0. Can I say? Yes, 28 mod 2 is also equals to 0 because the remainder of the division of 28 and 2 is 0. And the remainder of the division of 24 and 2 is also 0. So I can say that 2 is a potential answer. I have not explored anything else because there can be something even bigger than 2 that can be the answer. But for now, what I'm able to visualize is 2 is a potential answer. At least 2, we have something. We have some answer with us. Okay. Now the next question that you should ask is, if 2 is a potential answer, let's try to find something bigger than 2, right? So can 3 divide both A and B? Can 3 divide both A and B? How will you check? 28 mod 3 equals to 0 and 24 mod 3 equals to 0, can I say this is going to be false? Because 3 divides 24, this is going to be a yes, but this is going to be a no. 3 doesn't divide 28, right? 3 doesn't divide 28. So 3 cannot be our potential answer. Our potential answer is still 2. And again, I'm going to find something bigger than 2. So 3 is not the answer. How about we try with 4? Can 4 divide both A and B? How will you check it? 28 mod 4 is equals to 0 and 24 mod 4 is equals to 0. Can I say that? And this is going to be a true. This is going to be a true, right? Because 4 divides 28 also. 4 divides 24 also. So I can say that we have found a better potential answer. 2 was able to divide both of the things, but now we have something bigger than 2 that can divide both the numbers. And what is that number? Can I say 4? So what I will do, I will update my potential answer to 4. I will update my potential answer to 4. And I will keep on proceeding. I will keep on proceeding. I will check with 5. Can 5 divide both of them? No. Can 6 divide both of them? No. Can 7 divide both of them? No. 7 can divide 28, but 7 cannot divide 24. 8 cannot divide both of them. 9 cannot divide both of them, and so on and so forth. We'll keep on checking. Let's say we came to something like 21. Can 21 divide both of them? No. Can 22 divide both of them? No. Can 23 divide both of them? No. Can 24 divide both of them? No. Do you think we need to check something beyond 24? Because if you go to 25, we are damn sure it will never be able to divide 24 because it is greater than 24, right? So can I say that you have to repeat a process? You have to somehow repeat a process. And what is this essence of repetition of this process? What is the essence of repetition of this process? The essence of repetition of this process is that you check whether the first number can divide both of them. If that number can divide both of them, update your potential answer. This is a potential answer, but something bigger can be a better answer. So we'll try to go for something bigger. Can 3 divide both of them? Can 4 divide both of them? And so on and so forth. This can be a potential approach, right? And this can be very easily done using loops and if else, right? Because let's say you are at any number I and you have to check whether I can divide both of them. All you have to do is, if let's say this number is A, this number is B, you have to check if A mod I double equal to 0 and B mod I double equals to 0. If both of these conditions are true, then I can say I divides both of them. So I will store I inside my potential answer. Can I say that? As simple as that. This can be a very simple approach to go for. Now guys, there is a corner case of prime numbers. If you have two prime numbers, for example 7 and 11, then for prime numbers the answer is always going to be 1, right? Because prime numbers can only be divided by 1 or themselves. So for prime numbers, the HCF or GCD is always going to be 1. So can I say, as a note, can I say 1 will be our minimum answer? Can I say that? Because if we have any two numbers, the answer will be either 1 or something greater than 1. The answer will be 1 or something greater than 1. Because you cannot go less than 1 for a highest common factor or a GCD, right? So our answer will be at least 1 or something greater than 1. So if I want to write a code for it, what I can say is, let's say we write a function GCD A comma B. Okay, A comma B. Cool. We will initialize a variable let answer is equals to 1. Because answer will be at least 1, right? We will be having at least 1 as the answer. Okay. Then you say for let I is equals to 2. We are going to start dividing with 2. And we are going to go till I is less than or equal to. How can you calculate minimum of the two numbers? Either you can write your own custom function to calculate minimum of the two numbers very easily, or there is an already inbuilt function called as math.min a comma b. So in math.min a comma b, you can just pass math.min a comma b, and it is going to return you the minimum of the two numbers. It's an inbuilt function. We already know about inbuilt functions. And then I'll do I plus plus. Okay. I'm going to check if a mod I is equals to 0 and b mod I equals to 0. Can I say that? So I'm going to check whether I divides both a and b or not. If I divides both a and b, I can say answer is equals to I. Can I say that? Answer is equals to I. But the moment we find a number I that can divide both of them, we will update the answer variable. But we should not stop it. We should not stop here, because we can find something even bigger than I later in the loop. So we will keep on running the loop. We will keep on running the loop. We will not stop the loop anywhere. And at last, we can just say return answer. That's it. This is going to be a simple function using which you can calculate greatest common divisor of the two numbers, right? And the simple implementation is going to be as simple as that. So by just looking at the term greatest common divisor, we were able to solve this question. And to be very honest, the implementation is also going to be extremely easy. So in order to solve this question, I'm just briefly telling one more approach. This approach is called as Euclid's algorithm, right? This algorithm you will be learning later as well, right? And it requires a bit of mathematical concepts in order to solve the same question, to calculate greatest common divisor of two numbers a comma b. Okay, cool. Now, what is a common divisor? Or let's say, what is a divisor? Something that can divide a given number, right? For example, if let's say we have a number x is equals to 14, then we can say 2 and 7 are divisors, right? 2 and 7, both of them can divide the number 14. Can I say that? Now let's say we divide 33 with 5. Okay, we divide 33 with 5. How do you divide 33 with 5? You write something like this, right? 5 is the 5. We'll try to divide 5 with 33 with 5. We'll say 5 6 are 30. So 6 is the quotient, 3 is the remainder. Can I say that? This is how we do a basic division. In this basic division, can I write 33 is equals to 5 into 6 plus 3? Why? Because 5 6 are 30 plus 3 is 33. Yes or no? As simple as that. If I just generalize this term, if I just generalize it, to generalize, if we say we divide a with b, such that q is the quotient and r is the remainder. See, this is the quotient q, this is the remainder r. So can I say, if we divide a with b, can I write a is equals to b into q plus r? Can I write a is equals to b into q plus r? See, let's say 33 is a, 5 is b, 6 is q, 3 is r. Can I say a is equals to b into q plus r? As simple as that, right? And if we simplify this, this can be written as a minus bq is equals to r. Okay, a minus bq is equals to r. Okay, fair enough. Now, let's say GCD of a and b. This was our original question, right? You need to calculate GCD of a and b. Let's say GCD of A and B is some number capital G, right? Let's assume that the GCD of the given two numbers A and B is some number capital G, right? If capital G is the GCD of A and B, then A mod capital G is equals to 0 and B mod capital G is also equals to 0. Can I say that? Right? A mod capital G is equals to 0 and B mod capital G is equals to 0, because if it is the greatest common divisor, it will definitely divide both the numbers. See, what did I say? If you divide two numbers A and B, you can write it in the form A is equals to BQ plus R. How? See, 33 divided by 5, 5, 6 are 30. You get a remainder 3. So 5 into 6 plus 3 can be written as 33. If 33 is A, 5 is B, 6 is the Q quotient and 3 is the remainder R, you can write A is equals to BQ plus R. And then you can simplify it as A minus BQ is equals to R. Let's say this is equation number 1. Now we are assuming that for the given number A and B, let's say there is a GCD, some number GCD G. There is some number that is the GCD G. For example, let's say if you have 28 and 24, right? Then GCD of 28 and 24 is what? 4. Okay, cool. So what I can say, if G is the GCD, then G will completely divide A also. G will completely divide B also. Okay. Now let me ask you a question. What is BQ? What is BQ? You see this term BQ here? BQ is a multiple of B. Multiple of B. Can I say that? For example, if let's say B is 5 and Q is 6. 5 6 is 30. Right? So 30 is a multiple of 5, right? You can say it is a multiple of 5. Yes or no? So can I say if G divides B, that means B mod G is equals to 0. It implies that G divides the multiple of B. It implies that G divides multiple of B. For example, let's say the number is, let's take the number as 14. Let's say B is equals to 14. Can I say 2 divides 14? Can I say 2 divides 14? If 2 divides 14, 2 will also divide 14 into 2. 2 will also divide 14 into 3. 2 will also divide 14 into 4. 2 will divide all the multiples of 14. Can I say that? That's what I'm saying here. That if the GCD divides B and BQ is a multiple of B, because let's say B is 5, then 5 into 2 is what? A multiple of 5, right? Or 5 into 6 is what? A multiple of 5. So if G divides B, G will also divide multiple of B. Multiple of B. So I can write BQ mod G is also equals to 0. Can I say that? So if the greatest common divisor divides B, then the greatest common divisor will also divide the multiple of B. Okay. So now, what was our equation number 1? A minus BQ is equals to R. Okay. If you see the LHS, this is the LHS, this is the RHS, right? If you see the LHS, inside the LHS, A is divisible by G, and can I say BQ is also divisible by G? Divisible by G, right? A is divisible by G and BQ is also divisible by G. So can I say that this remainder R, because A minus BQ is equals to R, right? A minus BQ is equals to R. A is a number that is completely divisible by G. BQ is a number that is completely divisible by G. If you subtract these two numbers and you get a number R, then can I say R is also going to be divisible by G, let's say capital G, right? Capital G. Let's take an example. Okay. Let's say A is equals to 78. Let's say A is equals to 78. And let's say B is equals to 36. B is equals to 36. Okay, cool. If you divide 36 with 78, what you are going to say? 36 2s are 72. What is the remainder? Remainder is 6. So can I write this term as 78 is equals to 36 into 2 plus 6? Right? Can I say that? Can I say that? Okay. Now what is the GCD of 78 and 36? Let's go to an online calculator. Let's open an online calculator and see what is the GCD of 78 and 36. GCD of 78 and 36. Okay. The GCD of 78 and 36 is 6. Can I say that? See, online you will see. So if you write this as 78 minus 36 into 2, this value will be equal to 6. Can I say that? And we know that the GCD is 6. Now can I say 6 completely divides 78? 6 will completely divide 36 into 2 also. If 6 divides 78, 6 divides 36 into 2, 6 should also divide your RHS. And can I say 6 divides RHS? 6 by 6 is equals to 1, right? Or you can say 6 mod 6 is equals to 0. So this statement you can directly correlate, right? In the LHS, if all of the terms are divisible by a particular term G, then in the RHS also it should be divisible, because A minus BQ, this subtractive term is equals to R, right? This term of subtraction is equals to R. This subtraction is not going to make any changes in the divisibility, because A is completely divisible by G, B is also completely divisible by G. If you just subtract the component of the same divisibility, you will get a component which is also divisible by G, right? Now you might be thinking, okay, what is the conclusion? A minus BQ is equals to R. What you can say is, if G is the GCD of A and B, then can I say G is the GCD of A comma B comma R? Can I say that? Right? If I want to calculate the GCD of 78 and 6, that is also going to be 6, because now 6 is also going to be divisible by the corresponding number G, right? So the GCD is going to be same. And can I say A was greater than B? All of the assumption was made around the fact that A was greater than B. Then that's why I kept A here, right? So if A is greater than B and B is definitely greater than R, B is definitely greater than R, then can we somehow use this property? So let's say we have the number 78 and 24. I want to calculate what is the GCD of 78 and 24. I don't know what is the GCD of 78 and 24. Okay. Let's calculate the remainder of 78 and 24. What is 78 mod 24? What is 78 mod 24? Let's see. So I can just open JavaScript and JavaScript console, and this is going to be an easy thing to check, right? How can you calculate the remainder of 78 and 24? Something like this. What is the remainder? 6. Okay. So the remainder is 6. Now, initially, what was your problem? You wanted to calculate the GCD of 78 and 24. You know that the remainder of 78 and 24 is 6. So can I say whatever is the GCD of 24 and 6 will be the GCD of 78 and 24? Can I say that? Because all of them are going to have the same GCDs, right? So whatever is the GCD of 78 and 24 will be the GCD of 6 and 24. Okay. Now the problem boils down to calculate the GCD of 24 and 6. Let's calculate the remainder again. Let's calculate the remainder again. What is 24? What is 24 mod 6? Can I say it is 0? 6 4s are 24. So the remainder is 0. And if we have two numbers x and y, and you want to calculate GCD of x and y, GCD of x and y, and x mod y is equals to 0. Can I say GCD of x and y is y? Can I say GCD of x and y is y? For example, what is the GCD of 24 and 12? What is the GCD of 24 and 12? You can see 24 mod 12 is equals to 0. So the GCD will be 12 because the biggest number 12 will of course divide itself, and 12 also divides 24. Nothing beyond 12 can be our answer, right? So 12 is the biggest number that can divide both 12 and 24. And you can see here, right? You can see here that 24 and 6. 6 divides 24. What will be the GCD of 6 and 24? It can never be something greater than 6. It will be either 6 or less than 6. And 6 divides both of them. 6 divides itself. 6 divides 24. We want to find the biggest value. So 6 is the biggest value that divides both of them. Right? So what you can do is, if you have any two numbers a and b, what you can do? You can calculate their remainder, a mod b. Right? You wanted to calculate GCD of a comma b. You just calculate their remainder a mod b, and then you try to calculate the GCD of b comma r, that is technically a mod b. Then do the same thing, that let's say r2 is b mod r. Then go and calculate the GCD of r comma r2, and so on and so forth. You try to reduce these terms. Like this thing can be done anywhere. For example, let's say a is equals to 100 and let's say 105. B is equals to 36. Okay, B is equals to 36, A is equals to 105. Let's calculate the remainder. What is A mod B? What is 105 mod 36? 105 mod 36. If you run it, it is 33. Okay. So whatever is the GCD of 105 and 36 will be the GCD of 36 and 33. So now you go and calculate the GCD of 36 and 33. What is the new remainder R2? A mod B. What is 36 mod 33? It is 3. 36 mod 33 is 3, right? 33 ones are 36 and the remainder will be 3. So now whatever is the GCD of 36 and 33 will be the GCD of 33 and 3. And if you calculate R3, what is 33 mod 3 equals to? Is equals to 0. So the moment you find two numbers a and b such that a mod b is equals to 0, the GCD of these two numbers, can I say GCD of 33 and 3 is what? 3. And whatever is the GCD of 33 and 3 was the GCD of 36 and 33, that is 3. And whatever is the GCD of 36 and 33 will be the GCD of 105 and 36, that is 3. So our answer should be 3. And even if you go and calculate, what is the GCD of 105 and 33? The answer is 3, right? So this approach is called as Euclidean algorithm, right? The name is given to the scientist Euclid. So it's called as a Euclidean algorithm, that you keep on dividing the numbers, get their remainder, and then try to find the GCD with respect to the remainder. Because at last, somewhere down the line, the problem will reduce to something like this. And you can see this is a repetitive process, right? You first divide these two numbers, get a remainder. Then you again divide the numbers just by updating R to B and B to A. Then you again do this division. Then you again do this division, so on and so forth. So all of this division can be done via loops, right? You can just use some basic for or while loops in order to repeat this process, right? So this algorithm is called as Euclidean algorithm. When we will learn things around time and space complexity, that is how you can make your algorithms fast, then you will realize that this is the fastest way to calculate GCD of two numbers, even faster than the previous algorithm that we discussed, right? So I'm not going to code this for now. I want you guys to code it. Try to do some hands-on. I've shared you the whole approach. I've given you multiple examples. Last example was like having at least 3 iterations. So try to code it on your own. But this is something that you now know, that using Euclidean algorithm, you can calculate the GCD of two given numbers. Maybe further down in some lectures, I can maybe even code it and show you how you can calculate the GCD of the two numbers using Euclidean algorithm. So this is a new question in front of you. The question says that you have been given a number x and you need to calculate the sum of the digits of the number x, right? So let's say the number is 4136. This is the given number. The answer should be 14. Why? Because 4 plus 1 plus 3 plus 6. So 6 plus 4 is 10. 3 plus 1 is 4. 4 plus 10 is 14. So the sum of the digits of the given number is 14. So you will be given some number x. You need to write a code that can help you to calculate the sum of the digits of the number x. How can you do it? How can you do it? So if you see any given number and you want to calculate the sum of the digits of the given number, then there is one very basic thing that you need to always keep in your mind. If you want to get the digits of the number, you need to somehow extract all the digits. If we need the digits of, or I would say if we need the sum of digits of the number, we first of all need to extract the digits out of the number. We need to first of all extract the digits out of the number, right? We need to somehow separately get 4, 1, 3, 6. We need to separately get the access of all the numbers, or I would say all the digits, right? How can you get access to all of the digits? Let's try to understand that. So before we actually go into the logic, I would like to explain you guys about another inbuilt function. Which is math.floor, which will take a number x. So what math.floor does is, for example, if you pass 6.3 inside math.floor, it is going to return you 6. What it will do? It will just return you the integer part of the decimal number and avoid the part which is post the decimal. If you do something like math.floor 7, it is just going to return a 7. If there is no decimal part, no problem. If there is no decimal part, no problem. But if there is any decimal part, it is just going to eliminate the decimal part and it is going to return you the integer part out of it. So if let's say you pass 19.365 in math.floor, it is just going to return you 19, right? It is just going to return you 19. We don't need to technically go inside the fact that how they are actually doing it, because it must be a very simple, like if I have to implement my own math.floor, we can just do it very simply, right? And let's say if you have written 6.3, it is something like what? 63 divided by 10, right? So try to divide 63 with 10 and don't just try to eliminate the remainder. So from here, the quotient is going to be 6. So if you have to implement it on your own, so you can do it something like that. But for the time being, we can just assume the fact that they are just going to eliminate the decimal part out of it. Okay. Now, if we know this piece of information, let's come back. And let's say if we have the number 4136, right? If you have the number 4136, what will be the value of 4136 mod 10? If I will try to divide 4136 with 10, what will be the remainder? What will be the remainder? Can I say the remainder will be 6? Right? The remainder will be 6. Can I say that? Because 4136, if you try to divide with 10, you can have the quotient as 413. So it will give you 4130 and the remainder will be 6. Right? So if you have a number, if you have been given a number and you calculate the remainder that you will get after the division by 10, you do something like number modulo 10, that is try to get the remainder with division 10. Can I say you will be able to extract the last digit of the number? So if we do x mod 10, we get last digit of the number. We get the last digit of the number, right? Let's take one more example. Let's say you have 12683 and you do a mod 10. What will be 12683 mod 10? Can I say it will be 3? It will just give you the last digit. So I have the access of the last digit of the given number by just doing a mod 10. Can I say that? Okay. Coming back to the same example, 4136 mod 10 gives you 6. Okay. Now I have access to the last digit. But what about the remaining digits? What I can do for them? If I have the access to the last digit, let's do one thing. I can prepare a variable sum which is initially 0. What I will do? This is our given number x. I will do x mod 10. What is x mod 10? 6. What I will do? I will add 6 to the sum. Whatever is the remainder, I'll add that remainder to the sum. Okay. That means I have added the last digit to my sum. But what about the remaining digits? How can we get access to the remaining digits? How about we do something like 4136 by 10, 4136 by 10, and try to calculate the floor value of it. Okay. So what is 4136 by 10? 4136 by 10 will be 413.6. 413.6. And if you do a math.floor of 413.6, you are going to get 413. So can I say that using this operation, math.floor of x by 10, we were able to eliminate the last digit? Can I say that? By doing math.floor of x by 10, we can eliminate the last digit. Can I say that? And if you can eliminate the last digit, now you have 413. How about I repeat the process? So now you have 413. You again do mod 10, you get 3. You can add this 3 in your sum. So sum was, let's say, initially 0 plus 6. Now you got this 3. You add this 3 in your sum. So you added 3 in the sum. And then you again do math.floor of 413 by 10. This is going to give you 41. It is going to eliminate the last digit. Right. Then you repeat the same process again. You do 41 mod 10. You get a value 1. You add this 1 in your sum. And then you do math.floor of 41 by 10, which is going to be what? 4. And then you repeat the process again. You say 4 mod 10. What is 4 mod 10? It will give you 4. So you add a 4 here. And then you do math.floor of 4 by 10. 4 by 10 is 0.4. So this is going to give you 0. The moment you reach 0, we need to terminate here. We can terminate here, right? Because there is no point of pushing our algorithm post 0, because after getting a number 0, you cannot have any digits. It's not going to affect the sum. So we can stop here, right? So what I'm trying to say is there is an element of repetition. What is the element of repetition? For the given number x, calculate the remainder by 10, add that remainder to the sum, and then eliminate the last digit of x. And loop it again and again till the time x doesn't become 0. So what I can say is while x is greater than 0, that means we are having a value greater than 0. What you can do is, let's create a sum variable. Let sum is equals to 0. I'll code it also, don't worry. First of all, let's create a remainder. Let remainder is equals to x mod 10. Can I say that? X mod 10 will give me the last digit, or we can even name the variable as last digit. Let's do it like last digit is equals to x mod 10. Then we can add this last digit to our sum. Sum plus is equals to last digit. And then we can eliminate this last digit. So we can say x is equals to math dot floor of x by 10. And that's it. And at last we can just return the sum. Okay. Let's try to run this code. Let's try to dry run this code and then I will code it. Let's say x is equals to 4136. Okay. Let's say x is equals to 4136. I'm going to put a pointer here. That is what is the current line of execution. So we create a sum variable. So sum is equals to 0. Okay. We go to the next line. Is 4136 greater than 0? Is 4136 greater than 0? True. So we go inside the loop. We create a variable last digit. Last digit is equals to, what is last digit? X mod 10. What is 4136 mod 10? Can I say 6? Because it will give you the last digit. Then we go to the next line. Sum plus is equals to last digit. So we will add 6 in the sum. If you add 6 in the sum becomes 6. 0 plus 6 is 6. And then you update x with mat.floor of x by 10. So what is x by 10? 413.6. What is mat.floor of 413.6? 413. So you assign the value 413 back to x. So technically x now becomes 413. And then you go back to the looping condition. Is 413 greater than 0? Is 413 greater than 0? Yes. So you come here. Again, you have the last digit. Now the last digit is 413 mod 10, that is 3. Then you do sum plus is equals to last digit. So 6 plus 3 is going to be 9. Then you update x as mat.floor of x by 10. So what is 413 by 10? It is 41.3. And what is mat.floor of 41.3? 41. So you assign the value 41 to x, or you can say you eliminate the last digit. You go back. Is 41 greater than 0? Yes. You calculate the last digit. Now the last digit is 41 mod 10 is 1. You add it to the sum. So sum becomes 10. Sum becomes 10. Then you update x is equals to mat.floor of x by 10. X is 41. X by 10 is 4.1. Mat.floor is 4. So you assign the value 4 to x, or you can say we just eliminated 1. Then we go back. Is 4 greater than 0? Yes. We calculate the last digit. What is 4 mod 10? We can say 4. We add it to the sum. 10 plus 4 is 14. And then we say x is equals to mat.floor of x by 10. What is 4 by 10? 0.4. What is mat.floor of 0.4? Can I say 0? So x becomes 0. And now you check. Is 0 greater than 0? Is 0 greater than 0? No, right? So you come out of the loop and you return the value of the sum. Can I say that? So what did we do? We first added 6 to 0, then 3 to 0, then 1 to 0. 6 plus 3 plus 1 is 10. Then we added 4 to 10 and hence we got 40. So one by one we just extracted our digits. We added those digits to the sum and we eliminated the digits so that we can extract the next last digit. As simple as that. Now let's try to code this solution and see what can be done. So let's write a function sum of digits. This function will take a number x. We'll say let sum is equals to 0 while x is greater than 0. Okay, see, we are saying while x is greater than 0, let last digit is equals to x mod 10. So for example, if you have 4136 and you do a mod 10, you get 6, which is the last digit, right? You get the last digit. Now you add the last digit to your sum and you say x is equals to math.floor of x by 10. So let's say if you have 4136 by 10, this gives you 413.6 and math.floor of 413.6 is 413. So you eliminated the last digit. That's it. And at last you can return your sum. When the loop ends, you want to return your sum. You can do console.log sum of digits, and if you run it, you can see the answer is 14. We are getting the correct answer. So this is going to be a simple implementation to calculate the sum of the digits. So we have a new question in front of us. The question says that the above series of numbers are called as Fibonacci numbers. So if you see these numbers, these are Fibonacci numbers: 0, 1, 1, 2, 3, 5, 8, 13, 21, so on and so forth. These numbers are Fibonacci number, right? Given a value n, so the above series is called as Fibonacci numbers, and now the question is that you will be given a value n and you need to write a code to print the first n Fibonacci numbers. So what do you mean by when we say n Fibonacci numbers? So if you see this series, then inside this series 0 is considered as the 0th Fibonacci. So we count this counting from 0, right? We do the counting from 0. So 0th Fibonacci is 0. First Fibonacci is 1. Second Fibonacci is also 1. Third Fibonacci is 2. Fourth Fibonacci is 3. Fifth Fibonacci is 5. Sixth Fibonacci is 8. Seventh Fibonacci is 13. Eighth Fibonacci is 21, and so on and so forth. So if we say we want to print the first 10 Fibonacci numbers, and let's say n is 6. So you need to print 0, 1, 1, 2, 3, 5, 8. Up to the 6th Fibonacci number, you need to print everything. How can we solve this question? So if you carefully see the Fibonacci numbers, then if you skip the first two numbers, if you just skip the first two numbers and then check any number, so let's say we check this number 1, then every number is a sum of the previous two numbers. So 1 plus 0 gives you 1. Let's say this 2. So 1 plus this 1 gives you 2. 1 plus 1 gives you 2. If you see 3, then 2 plus 1 gives you 3. If you see this 5, 3 plus 2 gives you 5. If you see this 8, 5 plus 3 gives you 8. If you see 13, 8 plus 5 gives you 13. If you see 21, then 13 plus 8 gives you 21, right? If I want to write the next number after 21, so the next number here will be the sum of 21 and 13. What is 21 plus 13? Can I say 34? So 34 will be the next term of the Fibonacci numbers. Then if you want to write something beyond 34, then 21 plus 34 is what? 55. So 55 is the next Fibonacci number post 34. So this is the logic of the Fibonacci numbers, that apart from 0th and first Fibonacci, if we consider any Fibonacci number, then the number is actually sum of the previous two Fibonacci numbers. The sum of the previous two Fibonacci numbers. See, if you see this 8, 8 is 5 plus 3. If you see this 13, 13 is 8 plus 5. So can I say, if f of I is the ith Fibonacci number, if let's say f of I represents ith Fibonacci number, then f of I is equals to the sum of I minus 1th Fibonacci number and I minus 2th Fibonacci number, where I should be always greater than or equal to 2. Can I say that? See, starting from the second Fibonacci, every other Fibonacci follows this rule. The only thing is the first two Fibonacci, that is the 0th Fibonacci and the first Fibonacci, they don't follow it. And it makes sense, right? If you see, there are no two numbers behind the 0th Fibonacci, right? So how you will add anything? Same, if you see the first Fibonacci, so you have one number behind it, but you don't have the other number behind it. So these two values are actually the starter values. These are technically the starter values. Okay. These are actually the starter values. Cool. Now, how can you actually print the first n Fibonacci numbers? If I want to print the first n Fibonacci numbers, let's say I printed 0, I printed 1. These are the starter values, right? Okay. Then let's say I want to print 2. So I can just sum up the previous two values. So 0 plus 1 is 1 again. I will print 1. Then I will sum up the previous two values and I will get 2. Then I will sum up the previous two values. I will get 3. Then I will sum up the previous two values. I can get 5 and so on and so forth. Can I say that? So the element of repetition is every time add the previous two Fibonacci numbers and print the result. Okay. Now just think about it. If you want to always keep a track of the previous two Fibonacci numbers, you need to always also store them, right? So let's say we say that 1 is the last Fibonacci, 0 is the second last Fibonacci. If I want to print the next Fibonacci, can I say the sum of the last and the second last Fibonacci is 1? We will print 1, and then I will say that if I want to print Fibonacci number beyond this one, I will update my last and second last, because every time I'm just going to sum up the last and the second last. Now see, what is last plus second last? What is 1 plus 1? 2. So we will print 2, and we will say now the last printed Fibonacci is 2 and the second last Fibonacci is 1. Then we go 5, sorry, my bad. Then we go 3, because last plus second last, 2 plus 1 is 3. So we print 3, and now we say the last calculated Fibonacci is 3 and the second last calculated Fibonacci is 2. Then we again do the sum. 3 plus 2 is 5. We will print 5, and now the last printed Fibonacci is 5, second last printed Fibonacci is 3, so on and so forth. So we can say we can maintain two variables and keep a track of last and second last Fibonacci numbers, right? And keep a track of the last and the second last Fibonacci numbers. Can I say that? And that's it. And if we repeat this process, that add the last and the second last Fibonacci, so I added the last and the second last Fibonacci, I got 8. Whatever is the result, based on that, update the last and the second last Fibonacci. Can I say that? And that's it. This can be your logic, right? So we will repeat this logic again and again, and we will be able to print all the Fibonacci numbers, right? And till how many iterations do we need to do? How many times the repetitions we need to do? We need to repeat n times, as simple as that, right? So if I write a function print Fibonacci, and it takes a value n, that is the number of terms in the Fibonacci you want to print. Okay. First of all, maybe n can be equals to 0, right? Maybe somebody just asks you to print the 0th Fibonacci. So you can just manually do if n is 0, console.log 0, and you can return, right? Just think about it. Somebody can also give the input as 0, right? Let's say somebody gave n as 0. So all you need to do is just print 0 and that's it. You don't need to do anything beyond it. Same thing for n is equals to 1. If somebody gave you n is equals to 1, then you can say console.log 0 and console.log 1, and then you can return. Can I say that? These can be the two corner cases that we can handle. Just think about it. If somebody gave you n is equals to 1, all you have to do is just print 0 and 1. Because 0 and 1 are the starter values. They don't follow the Logic, the Fibonacci series, that every number is the sum of the previous two numbers. There are the starter or the seeder values. But now beyond this, what you can say is, let's make a new variable. Let last is equals to 1. Let second last is equals to 0. Let last is equals to 1 and second last is equals to 0. Can I say that? Let me make some space here. Okay. Let's make a bit of more space here. And let's put it here. Okay. The last Fibonacci is 1, second last is 0, because now you have something beyond 1. And now you can say you have already printed the first two Fibonacci numbers. We can assume that you have already printed the first two Fibonacci numbers, right? Or maybe what you can do is, we can even update this condition. Let's say here, first of all, you can just do console.log last, or maybe we can do one thing. If n is greater than or equal to 1, let's make sure. Let's say if n is greater than or equal to 1. So just think about it. If n is 1, you are going to print these two, and let's not return. Okay. And let's not return. I'll tell you why we are not returning here. You will realize in a minute. Okay. And now write a for loop. So for let I equals to 2, I less than equal to n, I plus plus. Why we are starting the loop from 2? Because we have already printed the two numbers. If let's say you want to print the first three Fibonacci numbers from 0 to 3, so you will come here. Is 3 greater than equal to 1? Yes. So you have already printed 0 and 1. Then you created a variable last, you created a variable second last, and then you can start iterating from the second Fibonacci number. So you can say let answer is equals to last plus second last. That is, you add the previous two Fibonacci numbers. Can I say that? You add the previous two Fibonacci numbers. You can do console.log answer, just print that Fibonacci number. And now for the next iteration, just think about it. Now let's say last Fibonacci number is 8, second last is 5. You added them, it became 13. So for the next iteration, you want to make sure that last should point to 13 and second last should point to 8, right? So how can you do it? You can say second last is equals to last. That is, first of all, make sure second last points to 8. Make sure second last points to 8. Why? Because if you will update last before updating the second last, you will lose the access to 8. Right? If let's say I update last to 13 and second last is still pointing to 5, we will lose the access to 8, right? So it's mandatory that you first update second last and then you update last. Last can be equal to answer, right? So now last can be equal to 13. So now you have access to last and second last. So you repeat the process and that's it. You can close the for loop here and that's it. You don't need to return anything from the function because we are just printing everything. Now you might be thinking why we are not putting a return statements here. Let's say if somebody gave you n is equals to 1. So you'll check. Is n equals to 0? No. Is n equals to 1? Is 1 greater than equal to 1? Yes. So you print 0, you print 1. Okay. You create these two variables. You start from here. I is equals to 2. Is 2 less than or equal to 1? No. So the whole for loop will not be executed and you would have just printed 0 and 1. That's it. That's it. So if I just code this solution, I'll write a function print Fibonacci, which will take a number n. First of all, if n is 0, I just need to print 0. I don't need to think a lot. I just need to print a 0 and return. But if n is something greater than or equal to 1, I need to print 0 also. I need to print 1 also. Right? And then what I will say is let last is equals to 1. Let second last is equals to 0. And then for let I equals to 2, I less than equal to n, I plus plus. We'll say let answer is equals to last plus second last. Then we print the answer, console.log answer. Then what do we say? We first update second last. So second last will become equal to the last Fibonacci, and the last value will become equal to the answer. That was the current Fibonacci that we calculated, and that's it. So if I call print Fibonacci for 5 and run it, see, we are printing 0, 1, 1, 2, 3, 5. That's it. 5 is the fifth Fibonacci. Makes sense. If I go for 0, I have just printed 0. Makes sense. If I want to just print Fibonacci up till the first Fibonacci, so 0 and 1 is getting printed. If I go for up till third Fibonacci, so 0, 1, 1, 2 should get printed, and that's it. If I ask you for 13th Fibonacci, for example, so all of the numbers are getting printed and absolutely fine. So this is how you can calculate, or you can say you can print the first n Fibonacci numbers. So let's start a quick dry run. So I will click on start debugging. Okay, so we have already printed 0 and 1. Now keep an eye on the last and the second last variable. Okay, cool. So now last is 1 and second last is 0. See, last is 1, second last is 0. Okay. Is the value of I less than or equal to n? Yes. N is 5, I is 2. So 2 is less than equal to n. You sum the last and the second last Fibonacci. So 1 plus 0 is 1. So see, the answer variable is 1. Can I say that? And you print the answer variable. So you printed 1. And now you need to update. Now last should point to 1 and second last should also point to 1, right? So first of all, we will update second last. So second last points to 1 and then last points to 1 again. Okay. And we go to the next iteration. Now last and second last Fibonacci both are 1. So 1 plus 1 should be 2, right? So answer should become 2. Answer is 2. Now you print the answer, printed the answer. And now second last should become equal to last and last should become equal to 2. So let's see. Second last remains 1 and last becomes 2. See, last becomes 2. Then we move ahead in the iteration. Now you see 2 plus 1. 2 is the last Fibonacci, 1 is the second last Fibonacci, 2 plus 1 is 3. You print 3 and now second last will become 2 and last will become 3. And so on and so forth. You can just keep on running it. And this is how you will get the first 5 Fibonacci numbers starting from the 0th Fibonacci number. So that was the debugging for the problem of print Fibonacci numbers, and I hope you guys are able to get the logic of how you can print the Fibonacci numbers.